We're going to go over the big O analysis of BSTs. One thing to keep in mind is we've already done this kind of from a more general look at the algorithms when we first introduced binary search trees. So you know that if you need to do search, insert, or remove on a binary search tree, that it's approximately log n. And you also know that when you need to traverse a binary search tree, whether that be in order, pre-order, post-order, all of those are O of n because you need to go through every node. And for the most part, that's kind of what you need to know. But we're going to continue to relook at analysis of our algorithms from like a little bit of a deeper level. One thing I wanted to point out, which some of you may have come across or been curious about, is the theory side of the big O analysis. So we're talking about big O in a very applied way. And we're not digging into the depths of theory and how we actually talk about big O. And we're also using a term actually technically incorrect, but that has been kind of colloquially accepted as a use of the big O term. So you don't need to worry about using this. It is actually how it's used, but technically and theoretically it is not. We are not using it correctly. But you won't learn about that till you take your algorithms class, which is CS401. I think, is the number. And so what I'm talking about is there's actually different versions of big O in Theoryland. There is big O, big omega, and big theta. And there's also little o. So big O would be the upper bound of an algorithm. Big omega would be the lower bound, and big theta would be the tight bound of the algorithm. And you'll learn about a little bit more about what those mean and how you actually can tell something like that. But technically, big O is something called a lower bound, which is almost impossible for you to understand at this point. So technically, when we say big O throughout this class, we're actually referring to big theta. But no one uses that term in the way that we're using it. Everyone says big O. So when you go and do interviews, when you go outside of this class, when people ask what the big O of an algorithm is, they're generally talking about big theta, which is what we're talking about. So continue to use big O, but I just wanted to add that detail in case any of you are interested, especially if any of you are really interested in theory. And don't worry about any of it because you will go into that when you take your algorithms class and you'll learn about what all those different things mean. One of the things that we like to talk about in this class, though, that is very similar to that conversation of the bounds of the algorithm, is talking about the different varieties of big O that you could even think about. So again, you can talk about big O in terms of space and time. We generally just talk about it in terms of time because most of the times the abstractions or the data structures we're using are only having one copy of the data. So it's big O is constant because it doesn't make extra copies. We've talked about a couple of algorithms like merge sort that makes a bunch of extra copies, but we haven't used it in anything so far, so it hasn't come up too much. The one way we do talk about space analysis all the time is in our programs we say you can't have additional copies of your data, you should only have one copy. And for a lot of the things that we're doing, that's what we're looking for. Time complexity, though, is something that we do talk quite a bit about because the choice of the abstraction or data structure sometimes makes huge differences in the complexity of the algorithm. So you can look at it a couple different ways. You can look at best case. So this is like what situation allows the least amount of computations to happen. Average case is like, well, what happens most of the time? If you take all the cases that are possible, what is the average case? What is the most frequent option that happens on average across the cases? What is the worst situation that costs the most? And then another one that we don't really talk about is the amortized option. which what happens over a period of time of running the algorithm many times. So we're going to look at some of these with some of the algorithms we talked about so you can think about it again. We're going to really dig into insert, and then we'll kind of highlight height just as an alternate option. As you know, insert has search in it, so we don't really need to do search. So let's think about what is the best case big O for insert. So the least expensive thing that we do with insert is we try to insert something that's already in a tree, because we've set up our insert function so that if it's there, then it's the easiest thing to do. We also want to consider the best case as not only inserting something that's already in the tree, but let's insert something that's at the root, right? That would be the easiest thing. So if we are trying to insert something that's at the root, we're going to set our cur pointer to root. We're going to, go into the while loop and run until it's not null, and then we check. If the root is the one that we're looking for, we find it on the first try and we return. So that's basically 5 operations. We're setting a couple pointers, we're doing one check, doing another check, and returning, right? So the best case is that you call insert on something that's not only already in the tree, but it's in the root. And so that's an example of what doing analysis on best case scenario is. It's kind of similar to what we were doing we did it a lot with vectors, right? So the best place to insert on a vector is at the back of the list, right? That's the cheapest, so that's an O1 insert. So this is 5 total operations, which is constant, right? No matter when you have to insert something, if it's at the root, it's always 5. Let's look at average case. So on average, what happens? So most of the time, we expect our binary tree to be reasonably balanced, meaning that you don't have like a really bad balanced tree would be one that just has like all the nodes to the left or all the nodes to the right. And we're going to talk about balancing trees next week, but most of the time we can ensure that our tree is reasonably balanced, meaning that the height of the tree is log of n, because we kept splitting by 2, with maybe a little bit of imbalance, which is what C indicates. So, this is an example of a tree that's not divisible by you can't turn it into powers of 2 exactly. So you have these 2 extra child nodes that don't equally fit into the height of the tree. And so that's what the C is. It's like whatever's left over, assuming that C is a lot smaller than n. So we'll just say that the height of our tree is log n plus C. And so on average, what can we expect? So we can expect that we might have to walk that whole tree, because most of the time we will have to, right? So for 1, 2, 3, 4, 5 of the nodes out of 9 of them, we have to go through the whole height of the tree in order to find them. So we have 2 operations that happen at the top no matter what. And then inside of the while loop, we have 1 operation, 2 operations, and then 3 operations that happen each time. And then inside of the if statement, depending on which one we go into, there's 2 more. So every time there's 5 in the while loop, and that can happen on average at log n plus C times, which is approximately the height. After that, we have 9 left over. So where did the 9 come from? Well, we have 1, 2, 3, 4. Then we have 5, 6, for that case. And then 5, 6, that would be if it was the new node. But actually, most on the average case times, you are actually going to go either left or right, because you're only going to have that case once when you're inserting the first node. So most of the time, you're actually going to go into this if statement, which means that you're going to check 1, 2, 3 times. So now we're up to 7. Some of these, we're just approximating, so you could even say that this is actually 2 operations, not 1. But anyway, that's 1, 2, 3, 4, 5, 6, 7. Because remember, most of the time that first if statement is actually false, because it's false for every case other than the first one. And then this is actually 2 operations because it's an increment and a variable assignment, and so that should be at least 9. So that's where we get the 9. So when we go through and really analyze the average case for this and work it all out, we basically get to 5 log n plus 5c plus 11. And as you know, we're going to end up dropping all of these to get the log n analysis. But this is a slightly more thorough analysis of a specific algorithm. So this is what you actually need to do when you analyze your algorithms, because you can say, oh yeah, I know that inserting into a tree is log n, but did you write your code in a way that you're actually doing that? Well, the only way to do it is if you actually work through the code and count everything up and make sure that that's true. Because a lot of times you might even be doing something inside one of these loops or inside one of these function calls that is actually not O1. What about worst case? So worst case is that your worst case is that your tree is imbalanced, basically. So this is assuming that we can, on average, keep our tree somewhat balanced, but if we can't, then we don't get log n, right? So if we have a tree that's really, really unbalanced, for example, completely unbalanced, it just becomes a linked list. So then everything we just did, we saw that the loop was 5 times. Now instead of being log n plus c, it's going to be n times, and then all the other operations are the same, the 2 at the start and the 9 at the back. And so worst case scenario for binary search trees is that you get a very unbalanced tree that basically converges to a linked list, and then you get 5n plus 11. So this is a summary of what we just did for best, worst, and average case. And so we can reduce the specific number of steps that we counted out when we did the analysis and just phrase them in terms of their order, which is best case it's O1, average case is log n, and worst case is O of n. So when we talk about big O, not only are we referring to big theta technically, which is a tight bound, but again, no one uses it, you can use big O. But we're also generally talking about our average case, because there's always going to be cases for worst case or best case that will be different than our average case. But we're also just generally wanting to be familiar with our algorithm. So if the worst case is always our case, so if we are building our trees so that they are very unbalanced and they're either exactly linked list or verging on linked list, then that is our complexity, right? So you have to really consider a lot more to your analysis than just assuming that all binary search trees are log of n. Insert. So what about traversal? What's the big O complexity of traversing a tree? Pre-order, post-order, in-order? As I said, traversals are always O of n. There's no way around it, right? If you need to go through all the nodes in your tree, then you have to go through all the nodes in your tree. So you can't make it more efficient. So you can't make it more efficient to delete a tree. You can't make it more efficient to copy a tree. You're kind of stuck with going through the whole thing. Or printing a tree, right? That's another case. So let's do height now. So for height, we are going to go through the best and the worst and the average case for height as well. And to do this, we're not going to be as thorough about counting up the operations, but it is a recursive call, so you should do that. It's a little bit tricky, but we're going to think about it more generally. So for the height, you can see that you have this like recursive call, right, to your function where you're going left, you're going right, and then you're doing something. So that's a traversal. And so that makes it seem like you're going to go through all the nodes, which you are. So the only way to know the height of your tree is to check all the nodes in your tree. You can't really, there's no really like quick way out. The only way is to visit each node and then do it in post order, so you can go up and then count up as you go. So what is the best case for calculating the height? Well, the best case is that you have an empty tree because it's really cheap to calculate the height of an empty tree, because if you look at the algorithm, you're going to pass in the root, and so if the root is null, then you're going to return out. So that's going to only have two operations, so that's going to be a constant complexity. So best case for counting the height on a tree is to have an empty tree. Otherwise, you basically have to go through all of the nodes, and there's really no way around it. There's a lot of operations that are happening as you walk through every tree. We can kind of count them up, but it's pretty tricky to think about all of them. So when you're at any particular node, what do you need to do in order to count it? Well, you need to go left and right, and that's going to have a couple operations. Going left is an operation, calculating the height is another operation. Returning back is another operation. Checking if it's null pointer is an operation, so we're already up to 7. Calculating out the max is an operation. Adding it to 1 is an operation, that's 9. Returning is another operation, that's 10. And there's probably other ones here and there. So it's definitely not just n, it's going to be something times n, right? But at every node, there's all these different operations, but you do have to go to each node. So even in worst case and average case, they're going to be the same. You're basically just going to have to go to each node. So there's not really a difference between worst case and best case because they're both going to require you to go through each node. So that is the big O of height. One thing to keep in mind for height is that there's no benefit to the shape of the tree. So unlike insert, having a balanced tree is actually much more efficient and much less complex in terms of our analysis. So our best case, or our average case, was assuming that we had a balanced tree, and our worst case was assuming that we didn't. With a height function, you have to visit every node anyway, so it doesn't really matter if the nodes are balanced or not. So that balancing really comes in handy when you have log n operations, not when you have n operations. So here's a summary of the complexity that we just went over with height. So that's all we're going to talk about with complexity of binary search trees. Space complexity, there's really nothing interesting about it. If you ever make copies of your tree, then you're going to have a non-constant space complexity, and if you don't, then you just have a constant space complexity for trees, just like all the other data structures. All right, so that's it.